All right, so this is my presentation on novel 3D Auxetic geometries for hip prosthetic applications designed using finite element analysis by Rizwan. So now, just to get in a little bit more about me. So my name is Rizwan, and I'm currently a rising senior over at John P. Stevens High School in Edison, New Jersey. And I'm currently working as a NASA summer intern over at Amos Research Center, and I also serve as the captain for my science bowl team at my high school. I'm also part of Team Prosthetics, which is where we ended up doing a lot of this work and the designs, which you will see in this presentation. And a notable achievement is that we were actually invited to present these designs and works over at the 20th World Congress of the ISPO, which was held last month. So now to begin, hip prosthetics are a critical global health issue, with over 1 million hip replacements performed each year globally. Ensuring these implants are strong, flexible, and long-lasting is vital to patient recovery and quality of life. Unfortunately, however, current materials used in hip joints often fail to mimic the complex movement of human tissue or absorb repeated impact well. Now, this leads to loosening, failure, and additional surgeries. That's where Auxetic materials come in, a unique class of metamaterials with properties that could dramatically improve prosthetic performance. So now, what are Auxetic materials? Well, Auxetic materials are defined by negative Poisson's ratio, meaning they expand laterally when stretched. This unusual behavior leads to better flexibility, enhanced energy, absorption, and increased resistance to impact, making them ideal for biomedical implants. Now, in the context of prosthetics, Auxetics can reduce implant micromotion, which helps minimize wear and bone resorption. However, most exciting is that auxetic structures are hard to manufacture and may concentrate stress, making them unsuitable for long-term load-bearing implants like the hip. And as a result, my team aimed to design novel hybrid auxetic geometries that overcome these challenges. We wanted to evaluate the structural performance of these designs using finite element analysis, or FEA, and determine which one is the best candidate for hip prosthetic applications. We also used a machine learning algorithm called a priori to identify which mechanical properties like stiffness or flexibility were most important for optimal performance. So first, we decided to design the hybrid geometries with three base geometries that are commonly used in prosthetic research, the reentrant, chiral, and star-shaped auxetic designs. Then we created three hybrids, a reentrant/star mix, a reentrant slash chiral mix, and a star slash chiral mix. Each was modeled using Fusion 360 and scaled to a 20 millimeter grid for simulation. These designs combine the best structural features from each base geometry to balance strength and flexibility. So now, in terms of our testing method, we decided to utilize finite element analysis, or FEA. We tested these models by applying a 10,000 Newton force, simulating the stress of a hip joint experienced during movement. We measured three key properties: effective Young's modulus, which indicates stiffness, Poisson's ratio, which reflects auxetic behavior, and last but not least, maximum displacement, which helps us understand flexibility. These values were input into a CSV file, which we ran through the a priori algorithm. This helped us determine which properties mattered the most in terms of creating a successful prosthetic. So now in terms of our results, we found that based on our analysis, Young's modulus received the highest weight of 2.0. It was the most important for resisting deformation. Poisson's ratio got a weight of negative 1.5 because we want to preserve the negative value that makes auxetic materials unique. Maximum displacement had a lower weight of 0.5 since too much flexibility can mean weakness. Ultimately, the reentrant/star hybrid outperformed all others. It had the highest stiffness of around 138 megapascals, maintained strong auxetic behavior of negative 0.7011, and resisted deformation the best, around 38.88% better than the original reentrant design. Over here in the table, you can take a look at our summarized results for Young's modulus, Poisson's ratio, and the maximum displacement for all three of the mixes that we tested. And of course, our one, which was the reentrant/star hybrid, was the most effective. So why does this actually matter? Well, this matters because stronger, more flexible prosthetics means fewer failures, fewer surgeries, and faster recovery. This design could lead to customizable 3D printed implants, which we are currently working on, that better match individual patient needs. And beyond hips, these materials could transform knees, spinal discs, and even cardiovascular devices. So in terms of our future work, we plan to incorporate more mechanical properties like tensile strength and fatigue resistance into our model. We also want to physically 3D print and test these prototypes to validate their computer simulations. And this bigger vision is by combining computational modeling with machine learning, so we can rapidly develop better, more adaptive materials for healthcare. And so I'll end off with this one question. How might these findings influence the next generation of prosthetic devices, and how can we ensure global access to them? In today's research, as we have currently performed, we saw that our novel Reintron and Star hybrid was the most effective, but how can we actually ensure that this does end up being implemented inside of current designs today and become more accessible for all types of people? Over here are my references for our work and our designs, and I would like to give big acknowledgments to Team Prosthetics, Mayank Dioras, Ishan Ghosh, Ayush Tripathi, Kartik Talam, and Veer Takal, as well as giving acknowledgments to RWJ Barnabas and Penn Medicine, Princeton Health for critiquing the designs and giving us feedback that was really essential for us to validate and actually perform a lot of our work. Thank you all for listening, and if you ever want to contact me, over here is my email and my LinkedIn. And again, I thank you all for listening.